This is another tutorial on Single SideBand Suppressed Carrier, and today the focus is going to be on types of Single SideBand Suppressed Carrier modulators. In my previous video, we discussed about how we're able to generate a Single SideBand Suppressed Carrier wave, and therefore we are going to discuss about the various types of which we can generate such wave. In general, we have two types. The first one is a frequency discrimination, and the second one is a phase discrimination. So let's talk about the frequency discriminator. So for the frequency discriminator, what we do is that we first generate a double sideband suppressed carrier AM wave. After generating it, we will get the output to be in both the two sidebands, that is the upper sideband and the lower sideband. When we get the results, we then pass the output or the Ssbsc generated wave through bandpass filter that has its center frequency, the one that we want. If we want the lower sideband, we tune the lower sideband in such a way that its frequency range will be between the range of the low pass filter. So in that case, it will allow it to pass. When it allows it to pass, it produces an output which is a single sideband suppressed carrier. So what we have to do is that if we want to produce a single sideband suppressed carrier as an output, we select our frequency range of which will fall within the range of the low pass filter or the band pass filter that we want to use. And in that case, we will be able to allow the Ssbsc output to go. So in all, you can tune the band pass filter device that we use to either lower sideband or an upper sideband frequency in such a way that when we want the upper sideband, we will tune the low pass filter in such a way that we are going to get the frequency range within the upper sideband frequency range, which will allow the upper sideband frequency range to go, leaving the lower sideband out. Therefore, we have been able to suppress both the lower sidebands and the carrier. Remember that the double sideband suppressed carrier production was able to suppress the carrier and then passing it through a bandpass filter having a range of frequency for the upper sideband will also allow the upper sideband frequency or wave to go, leaving the lower sideband out. The same thing applies to the lower sideband. If you want to get the lower sideband as your Ssbsc output, you tuned the filter in such a way that its frequency range will fall within the lower sideband frequency range. And in that case, we will be able to allow the lower sideband frequency to pass, leaving the upper sideband out. Of which you will be able to see that we have been able to suppress both the carrier frequency and the lower sideband frequency. That is generally about the frequency discriminator, and here is the block diagram for it. So this is a product modulator PM. Remember that when we are generating a double sideband signal or wave, we pass the message signal and then the carrier signal, of which this modulator will multiply these two signals, and the resulting output will be passed to the bandpass filter. So this one generates a Ssbsc signal for us. After generating it, it's then passed through a bandpass filter with its frequency range, which will be at our desired output. So now the output is going to be a single sideband suppressed carrier wave. So as I explained earlier on, remember that our C of t, it's the carrier wave which is having a formula A of c cos omega ct. And this carrier signal has a higher frequency, and that's the one that we are using to modulate our message signal, M of t. I was explaining earlier that if you want the upper sideband as your Ssbsc output wave, you need to tune this bandpass filter in such a way that its frequency range will fall within the upper sideband frequency range. And in that case, it will allow the upper sideband signals to pass, whilst attenuating the other frequency ranges. Same thing applies to the lower sideband. When you want the lower sideband to pass as our Ssbsc wave, we tuned the bandpass filter in such a way that each frequency range will fall within the lower passband frequency range, and therefore we'll be able to get it as an output. So let's look at how you can use the frequency discrimination method to generate a single sideband suppressed carrier wave. For the first discrimination method, we need two product modulators, which is modulator 1 and modulator 2. We use the same local oscillator, which is the source of our carrier signal. And this local oscillator will go directly into one product modulator, but the other product modulator will be phase shifted before we get into the other product modulator. The same thing applies to the message that we will put in the other modulator. When we are putting the message into the modulators, the first modulator, the message will go in directly, but the second modulator, we need to phase shift the message signal in order to put it into the phase modulator. And this is how we will be able to generate a single sideband suppressed carrier signal using the phase discrimination method. So without wasting much time, let's quickly draw the block diagram to illustrate what we are talking about. So as I said, we need two modulators, which is a product modulator, so PM1, and then we need another modulator, which is PM2. This is our message signal. It's going to this modulator, M of T. As the name suggests, phase shift. Remember that cos theta minus 90 is equal to sine theta. And therefore, this is what we are going to refer to as our phase shift. So if it's being phase shifted by minus 90 degrees, we will have the resultant output to be sine theta. So in this case, you have M of T, which is equal to AM cos omega MT. This is our local oscillator, which is LO. This local oscillator produces a carrier wave signal, and this carrier wave signal is being multiplied by the message signal going to the first modulator, which is AC cos omega CT. But when going into the second modulator, it's being phase shifted by minus 90 degrees. So when we phase shift this by minus 90 degrees, it's going to be AC cos omega CT, or omega C minus 90 degrees, or T. This is the phase shift. We have phase shifted this signal, and we all agree that it's equal to sine omega CT, as I illustrated over here. So now this local oscillator produces a carrier signal which is phase shifted by minus 90 degrees, and the resultant is going to be AC sine omega CT. The same thing applies to the message signal. We need to phase shift the message signal by minus 90. And remember that the message signal is AM cos omega MT. So when we phase shift it, we are going to get AM cos omega M minus 90 T. And we all agree that this is going to give us AM sine omega MT. So this is what we call minus 90 degrees phase shift. And therefore, that is what is being fed into the product modulator 2, which is AM sine omega MT. Now, this is what is going to be our result. The output of this modulator is being named X1 of T, and then the output of this modulator is being named X2 of T, because here we have our carrier signal and we have our message signal and being modulated by a product modulator which will produce a double sideband suppressed carrier output. Here is also producing a double sideband suppressed carrier output, Ssbsc. And then the resultant will come here to an adder. And this adder will have plus or minus here and plus here. So depending on the condition of this signal coming here, we will get either a low band pass or a high band pass. What I'm trying to say is that depending on the condition of this signal, which is minus or plus or minus, we are going to get a lower sideband as our single sideband suppressed carrier, or an upper sideband as our single sideband suppressed carrier. So basically this is our output S of t. So in summary, what I'm trying to say is that in doing a phase discriminator method, you need the message signal and the carrier signal. Aside that, we need two product modulators. Both modulators are producing double sideband suppressed carrier signal wave at the end. As you can see, this local oscillator here is producing the carrier signal, of which is being fed into the product modulator 1. That same output of the local oscillator, which is the AC cos omega ct, is being phase shifted and then fed into the product modulator 2. We do same for the message signal. We supply the message signal to the product modulator 1, and then we phase shift it by minus 90 degrees here to then supply it to phase modulator 2. And the output will be produced as a double sideband carrier suppressed carrier signal. When you are done, what we are going to do next is that for the x1 of t, the message is in cos, so we are going to get am cos omega mt multiplying by AC cos omega ct. And at the end of the day, we got am AC cos omega mt cos omega ct. For the x2 of t, when we phase shift the signals, we get am sine, and therefore we are going to get S2 of t to be am sine omega mt multiplied by AC sine omega ct. At the end of the day, we are going to get am AC sine omega mt sine omega ct. This is our x1 output and then x2 output of both modulators. From one of my previous tutorials, we came up to a point that our cos omega ct cos omega mt can also be written as 1 over 2 into bracket cos omega c plus omega m or t plus cos omega c minus omega m or t. This is what we arrive at. For sine omega mt, sine omega ct, the only thing that will change is the summation over here. So we are going to get 1 over 2 into brackets cos omega c plus omega m t minus cos omega c minus omega m t. So at the end of the day, the first output will give us am AC divided by 2 cos omega ct plus omega mt plus am AC over 2 cos omega c minus omega m or t. This is my first output S1 of t from one of the modulators, and then my second modulator S2 of t is equal to 1 over 2 multiplied by AM AC cos omega c minus omega or plus omega m or t minus AM AC over 2 cos omega c minus omega mt. So when we add x1 plus s2, which is being illustrated here depending on the sign, we can see that this one will cancel this one. At the end of the day, we are going to get this and this. When we add them, the total S of t is going to be AM AC cos omega c plus omega m or t. So this is our single sideband suppressed carrier. If you want to get the lower sideband, or let's say the lower sideband aspects, the only thing that we need to do is to subtract x1 minus x2. And in that case, the one involving cos plus here will be cancelling out because one will be negative and here will be positive. So when you add it up, you are going to get x of t to be equal to AM AC cos omega c minus omega m or t. This is when you subtract x1 minus x2. That is where this side is negative. So this is how you can use the phase discrimination method in generating a single sideband suppressed carrier signal. And all of them, they are having a bandwidth to be equal to FM, which is equal to the frequency of the modulating signal. So thank you for watching and see you in my next video.